This is the third module of chapter 7. In this module, we shall consider Gaussian quadrature methods. In Newton-Cotes quadrature formula, we have seen that particular formula cannot be used to find the integration of improper integrals. But the Gaussian quadrature formula can be applicable or can be applied to improper integral also. In Gaussian quadrature, the nodes, that means the values of x, may or may not be equal. In general, these nodes are unequal, unlike Newton-Cotes quadrature formula. But the Gaussian quadrature formula depends on the several weight function or several orthogonal polynomials. Now, we consider two orthogonal polynomials or two types of Gaussian quadrature formula. First one is known as Gauss-Legendre quadrature formula, and second one is known as Gauss-Sebeshев quadrature formula. The Gaussian quadrature formula is of the following form: integration a to b psi x fx dx equal to summation I equal to 1 to n wy into f of xi plus error, where xi and wy are respectively called nodes and weights, and psi x is called the weight function. Here wi's are the discrete numbers, but the weight function psi x is continuous and defined over the interval a b. In Newton-Cotes quadrature formula, the weight function were unknown, but the nodes, that means the values of xi's are known, while in Gaussian quadrature both are unknown. Therefore, by changing the different weight function, one can derive different quadrature formula. The fundamental theorem of Gaussian quadrature formula is stated below. The optimal nodes, that means the values of x of the n-point Gaussian quadrature formula, are precisely the zeros of the orthogonal polynomial, corresponding orthogonal polynomial for the same interval and weight function. This is the fundamental things of Gaussian quadrature, and we shall shown that the Gaussian quadrature gives exact results for all polynomial up to degree 2n minus 1 if we consider n points, n nodes and n weights. Suppose the Gaussian nodes xi's are chosen by some way, that means we assume that the values of xi are known. Then the weight wi's can be computed by using Lagrange interpolation formula. Let pi x equal to product of j equal to 1 to m x minus xj, and its derivative is given by equation 2. Then the Lagrange interpolating polynomial for m arguments given by equation 3 for any arbitrary x. Now, from equation 1, integration a to b phi x psi x dx, phi x is replaced by fx, which is equal to integration a to b summation j equal to 1 to m into this expression. This is nothing but the values of li into f of xj dx, and now interchange the summation and integration, we obtain equation 4, and the 8 mark portion is nothing but wj. The 8 mark portion is denoted by wj, that means wj is given by equation 6. This expression gives the values of all weights wj, j equal to 1 to m, and this expression depends on the weight function psi x and the expression or the polynomial pi x and the limit of the integration a to b. So, using this expression we can determine all w's, and this is the general expression to calculate the weights of Gaussian quadrature. Now, we consider a particular quadrature formula, Gaussian quadrature formula known as Gauss-Legendre quadrature formula. For this formula, the weight function psi x is taken as 1. So, in this case, the formula 1 is reduces to integration minus 1 to 1 fx dx equal to summation I equal to 1 to n wy f of xi plus e. Note that any finite interval can be transferred to the interval minus 1 to 1, but the infinite interval cannot be transferred to any finite interval like minus 1 to 1. by straightforward, but by replacing x by 1 by x, one can change the infinite interval to finite interval. Here wi's and xi's are twice n unknown parameter. These are called the parameters in this case. Therefore, wi's and xi's are determined in such a way that the above formula, that means equation 7, gives exact result when fx is a polynomial of degree up to 2n minus 1. So, for this purpose, or to determine the values of w and x, we consider a polynomial fx equal to c0 plus c1x plus c2x square up to c2n minus 1 x to the power 2n minus 1. So, this is a polynomial of degree 2n minus 1. Now, the left hand side of equation 7 is integration minus 1 to 1 fx dx equal to integration minus 1 to 1 the value of the integration function fx, and after integration, term by term integration, we get 2c0 plus 2 by 3 c2 plus 2 by 5 c4 plus dot dot dot. And when x equal to xi, the equation 8 becomes f of xi equal to c0 plus c1 xi plus c2 xi square plus dot 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 plus c2n minus 1 into xi to the power 2n minus 1. Now, the right hand side of equation 7 is summation I equal to 1 to n wi fx I. This is the right hand side of equation 7, and after expanding this expression, we get w1 into f of x1 plus w2 into f of x2 plus w3 into f of x3, and lastly wn into f of xn. The value of f of xn is c0 plus c1 xn plus c2 x1 to the power 2 plus dot 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 plus c2n minus 1 into xn to the power 2n minus 1. And rearranging this expression, we get the entire expression or equation 10 equal to c0 into w1 plus w2 up to wn plus c1 into w1 x1 plus w2 x2 plus dot 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 wn xn, and lastly plus c2n minus 1 into w1 x1 to the power 2n minus 1 plus w2 x2 to the power 2n minus 1 plus dot 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 plus wn into xn to the power 2n minus 1. So, equation number 11 is the right hand side of equation 7. Hence, the equation 7 becomes this one, equation 12 is the simplified form of equation 7. Now, comparing both sides of this equation, for the coefficient of CIs, we obtain the following 2n equations. The first one is w1 plus w2 plus dot 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 wn equal to 2. This one obtained by comparing the coefficient of C0. This one is obtained by comparing the coefficient of C1. This one obtained from the coefficient of C2. This one from the last one is obtained from the coefficient of C2n minus 1. So, this is a system of equations. That means equation 13 is a system of equation, highly nonlinear equations, contains 2n unknowns. N unknowns are w1 to wn and another n unknowns are x1 to xn, and the number of equation is also 2n. So, solving this equation, we can determine the values of all w's and all x. So, after computing the all x and all w, we can find the Newton Gauss-Legendre quadrature formula, but it is very difficult to find the general solution of equation 13 for general values of n. So, for this reason, we consider particular values of n. Now, we consider n equal to 1 as case 1 to get a particular Gauss-Legendre quadrature formula. In this case, the formula is integration minus 1 to 1 fx dx equal to w1 into f of x1, and the corresponding system of equation is w1 equal to 2 and w1 into x1 equal to 0, that is x1 equal to 0. Hence, for n equal to 1, the Gauss-Legendre quadrature formula is given by equation 14, which is nothing but integration minus 1 to 1 fx dx equal to 2 into f0. Note that this is a very simple formula to find the integration of any function fx, of an integrable function fx, and that value is the value of the functional values at 0 into 2. This formula is known as one-point Gauss-Legendre quadrature formula, and it gives the exact answer when fx is a polynomial of degree 1. In case 2, we consider n equal to 2. for this value, the Gauss-Legendre quadrature formula is this one given by equation 15. Here W1 and W2 are two weights and x1 and x2 are two nodes. The values of W1 and W2 and x1 and x2 are given by equation 16. These are the four equations containing four unknowns. The above system of equations can also be obtained by substituting fx equal to 1, x, x square and x cube to the equation 15. And solving this equation, we get W1 equal to W2 equal to 1 and x1 equal to minus 1 by root 3 and x2 equal to 1 by root 3. Thus, in this case, the Gauss-Legendre quadrature formula becomes minus integration minus 1 to 1 fx dx equal to f of minus 1 by root over 3 plus f of 1 by root over 3. That means equation 17 is the Gauss-Legendre quadrature formula for n equal to 2, and this formula is known as 2-point Gauss quadrature formula and gives exact answer when fx is a polynomial of degree up to 3. Now, for n equal to 3, the formula is given by equation number 18, and the system of equation containing 6 unknown x1 to x3 and w1 to w3 given by this 6 equation. This 6 equation can also be obtained by substituting fx equal to 1, x, x square up to x to the power 5 to the equation 18. Now, solving this system of equation, we get x1 equal to minus root over 3 by 5, x2 equal to 0, x3 equal to root over 3 by 5 and w1 equal to 5 by 9, w2 equal to 8 by 9, w3 equal to 5 by 9. So, using these values, we obtain equation 19. So, this equation, that means the formula given in equation number 19 is known as 3-point Gauss-Legendre quadrature formula, and this formula gives exact result for the polynomials whose degree is up to 2n minus 1, that means 6 minus 1, that means up to degree 5. It is very interesting that the nodes, that means the value of xi's, are the zeros of the n degree Legendre polynomial given by Pnx equal to 1 by 2 to the power n factorial n, nth derivative of x square minus 1 power n, and this supports the Gaussian fundamental theorem for Gaussian quadrature. And this polynomial is obtained from the recurrence relation written in equation number 20. And the particular values of this Gauss-Legendre polynomial are P0 x equal to 1 and P1 x equal to x. It can be verified that the roots of the equation Pnx equal to 0 are the nodes xi's of the n-point Gauss-Legendre quadrature formula. It is obtained from the statement mentioned in previous slide. For example, the roots of the equation P2x equal to 0 are plus minus 1 by root 3, and these are the nodes for 2-point Gaussian quadrature formula. We have already deduced these values. Similarly, the roots of the equation P3x equal to 0 are 0, plus minus root over 3 by 5, and also these are the nodes of the 3-point Gaussian quadrature formula. Again, it is proved that the weights wi's can be determined from the following equation, that means wy equal to 2 by 1 minus xi square into Pn derivative, that means derivative of first derivative of Pn at xi power 2. This expression gives the weights of all the Gauss-Legendre quadrature formula. Now, this table gives the values of xi and wi's for different points Gauss-Legendre quadrature formula. For n equal to 2, the nodes are plus minus 0.5773527 and weights are 1, and order of truncation error is f4 xi, that means fourth derivative of f at xi. This truncation error indicates that the 2-point Gauss-Legendre quadrature formula gives exact answer when the integrand is a polynomial of degree up to 3. And for n equal to 3, the nodes and weights are given by these expressions or given by these values, and the truncation error is 6th derivative of f at xi, that means n equal to 3, that means 3-point Gauss-Legendre quadrature formula gives exact result for the polynomials up to degree 5. These are the nodes and weight for n equal to 4, that means 4-point Gauss-Legendre quadrature formula. These are the nodes and weight for n equal to 5, and these are the nodes and weight for n equal to 6. Note that the truncation error, order of truncation error of 6-point Gauss-Legendre quadrature formula is 12 derivative of f at xi. That indicates that if the integrand is a polynomial of degree up to 11, then 6-point Gauss-Legendre formula gives exact answer. So, using a very few number of calculation, we get a more accurate answer or exact answer using 6-point Gauss-Legendre quadrature formula. So, we can conclude that the Gauss-Legendre quadrature formula is more better than the Newton-Cotes quadrature formula. Now, we consider one example. Here we have to find the value of the integration 0 to 1 x square sin x dx by Gauss-Legendre formula for n equal to 4 and 6. Also, we have to calculate the value of absolute error. Here note that the given integral, the limits of the given integral are 0 and 1, but the Gauss-Legendre formula is applicable for the limit -1 to 1. So, you have to transfer the integrand by a suitable variable x equal to half u into 1 minus 0 plus half into b plus a actually, which is equal to half into u plus 1. So, using this substitution we can transfer the given limits to -1 to 1. Therefore, I equal to integration 0 to 1 x square sin x dx, it's converted to -1 to 1 integration -1 to 1 1 by 8 u plus 1 power 2 sin u plus 1 by 2 du. And as per Gauss-Legendre formula, it is equal to 1 by 8 I equal to 1 to n wy f of ui, where f of xi equal to xi plus 1 power 2 into sin of xi plus 1 by 2. Now, for n equal to 4, that means 4-point Gauss-Legendre formula gives x1 equal to this value, x2 equal to this value, x3 is equal to minus x1, x4 equal to minus x2, and w1, w3 are equal and they are equal to 0.65, 21, 4515. w2 and w4 are equal, the values are 0.34, 78, 5485. Then I equal to 1 by 8 into w1 f of x1 plus w3 f of x3, w2 f of x2 plus w4 f of x4, and after simplification or after substituting the values of w1 to w4 and f of x1 to f of x4, we obtain this expression, and after simplification it is nothing but 0.22324429. This is the value of the given integration using 4-point Gauss-Legendre quadrature formula. Now, when n equal to 6, that means 6-point formula gives x1, x2, x3, x4, x5 and x6, and these are the values of w's, that means the value of weights. Then I equal to 1 by 8 w1 into f of x1 plus f of minus x1 plus w2 into f of x2 plus f of minus x2 plus w3 into f of x3 plus f of minus x3. And using the values of w1 to w3 and x1 to x3, we obtain this expression. After simplification, the value of I is 0.22324427. So, this value is obtained by 6-point Gauss-Legendre quadrature formula. The exact value of the integral is 0.22324428. Now, we compare the values obtained by 4-point Gauss-Legendre formula and 6-point Gauss-Legendre formula, and the exact value we get this table. For n equal to 2, this value is calculated in the text. The exact value is this one. Gauss-Legendre formula gives 0.22531632. That means the absolute error is 2.07 into 10 to the power minus 3. And for n equal to 4, the absolute error is 0.01 into 10 to the power minus 6. the error is very less compared to n equal to 2. That means 2-point Gauss-Legendre formula gives more error than the 4-point Gauss-Legendre formula. And also for 6-point Gauss-Legendre formula, the error is, absolute error is 0.01 into 10 to the power minus 6. The order of error in 4-point and 6-point formula is same. The general Gaussian quadrature formula is introduced, and a particular case of Gaussian quadrature formula called Gauss-Legendre quadrature formula is derived. And for different values of n, we derive 1 point, 2 point, 3 point, 4 point, 5 point and so on, different Gauss-Legendre quadrature formula. And we have observed that the Gauss-Legendre quadrature formula gives more accurate answer than the Newton-Cotes quadrature formula using less number of computation. Now, we consider another Gaussian quadrature formula called Gauss-Sebeshев quadrature formula. This formula is also based on a particular weight function, and the weight function is 1 minus x square to the power minus half. Now, we consider another Gaussian quadrature formula known as Gauss-Sebeshев quadrature formula. In this formula, the weight function is 1 minus x square to the power minus half. The general form of this method or of this formula is integration minus 1 to 1 by root over 1 minus x square fx dx equal to summation I equal to 1 to n wi f of xi plus some error term. Here also the number of parameters, that means wi and xi is twice n. So, as per Gaussian quadrature, this method gives exact answer for the polynomials of degree up to 2n minus 1. Now, we consider a particular case when n equal to 3. So, for n equal to 3, the equation 22 becomes integration minus 1 to 1 by root over 1 minus x square, this is the weight function, fx dx equal to w1 into f of x1 plus w2 into f of x2 plus w3 into f of x3. Now, we have to determine the values of w1 to w2, w3 and x1 to x3. Since this method gives exact value for the polynomials of degree up to 10 minus 1, that is up to 5. Therefore, for f of x equal to 1, x, x square, x cube, x4, x to the power 5 gives the exact answer obtained from equation 23. So, for fx equal to 1, we obtain from equation 23 the equation w1 plus w2 plus w3 equal to pi. When fx equal to x, then equation 23 gives w1 x1 plus w2 x2 plus w3 x3 equal to 0. And for other values of f, that means for fx equal to x square, x cube, x4 and x5, we obtain the remaining 4 equations. See that all these equations are highly nonlinear. Nonlinear with respect to x, that means if the values of x are known, then the equations, all these equations becomes a system of linear equation containing only w1, w2 and w3. So, solving this equation, we get x1 equal to root 3 by 2, x2 equal to 0 and x3 equal to minus root 3 by 2, and the w1, w2, w3 are equal and the value is pi by 3. Thus, the equation 23 becomes integration minus 1 to 1 by root over 1 minus x square into fx dx equal to pi by 3 into f of root 3 by 2 plus f0 plus f of minus root 3 by 2. So, this is the 3-point Gauss-Sebeshев quadrature formula, and this formula gives correct answer for the polynomials whose degree up to 2n minus 1, that means up to 5. Like Gauss-Legendre quadrature formula, many Gauss-Sebeshев quadrature formulae can be derived for different values of n. For n equal to 1, we can derive 1-point Gauss-Sebeshев quadrature formula. For n equal to 2, we can derive 2-point Gauss-Sebeshев quadrature formula and so on. In Gauss-Sebeshев quadrature formula, the nodes xi are the zeros of the Sebeshев polynomial. Equation 25 is the Sebeshев polynomial of degree n, that means Tnx equal to cos of n cos inverse x. That is, the nodes xi are given by the equation xi equal to cos of 2i minus 1 into pi by 2n for all I equal to 1 to n. That means when xi is given by equation 26 and the value of xi is substituted in equation 25, then Tn xi becomes 0. And the weight wi are same for all values of I. This is very interesting, and these are given by equation 27. That means wi equal to pi by n. The general formula is minus pi by Tn plus 1 xi, and derivative of Tn at xi. After simplification, it reduces to pi by n. So this is very simple formula, and it can be remembered for all values of n and all values of I. The values of nodes and weight for first few Gauss-Sebeshib quadrature formula are listed below. For n equal to 2, the nodes xi are plus minus 0.7071068 and weights are equal. This is nothing but pi by 2. And order of truncation error is fourth derivative of f at xi. That means 2-point Gauss-Sebeshib quadrature formula gives correct answer for the polynomials whose degree up to 3. And these are the nodes and weight for n equal to 3. Truncation error is of order f6 xi. For n equal to 4, the nodes and weights are this. It may be noted that the weights are nothing but pi by 4. Truncation error is f8 at xi. And for n equal to 5, the nodes and weights are given by these values, and truncation error is f10 at xi. That means the 5-point Gauss-Sebeshib quadrature formula gives exact result for the polynomials whose degree up to order or up to 9. Now we calculate the integration 0 to 1, 1 by 1 plus x squared dx by Gauss-Sebeshib 4-point quadrature formula. For this, let fx equal to root over 1 minus x square, the reciprocal of the weight function, by 1 plus x square. For this case, that means for n equal to 4, x1 equal to minus 0.3826834, which is equal to x2, and x3 equal to minus 0.9238795, which is equal to minus x4, and w1 to w4 are equal, and these values are nothing but pi by 4. Then the integration I equal to 0 to 1, 1 by 1 plus x squared dx, which is converted as half into minus 1 to 1, integration minus 1 to 1, 1 by 1 plus x squared dx. Note that the integrand is even function, so the entire integration is multiplied by half, and the interval is extended to minus 1 to 1. And this integral can be taken as half into integration minus 1 to 1 fx by root over 1 minus x squared dx. In terms of f, the integration is written in this form. And using the 4-point formula, we obtain this expression, and after simplification, it becomes 0.7950767. And the exact value is pi by 4, which is equal to 0.7853982. Therefore, the absolute error is 0.0096785. That means the integration is correct up to 2 decimal places. So this value is obtained from 4-point Gauss-Sebeshib quadrature formula. In this module, Gaussian quadrature formula is introduced. Two particular type of Gaussian quadrature formula. First one is known as Gauss-Legendre quadrature formula. For the weight function psi x equal to 1 is introduced, and another Gaussian quadrature formula known as Gauss-Sebeshib quadrature formula is introduced for weight function 1 minus x square to the power minus half. For other weight function, one can derive other Gaussian quadrature formula, and several Gaussian quadrature formula are available in literature. We have seen that the Gaussian quadrature formula gives more better and accurate result compared to Newton-Cotes quadrature formula. These formulas, that means Gaussian quadrature formulas, are applicable for proper and improper integrals. But for first type improper integral, the Gaussian quadrature formula cannot be applicable, but by changing the independent variables, that means x is replaced by 1 by x, one can convert the interval, infinite interval, to a finite one or to minus 1 to 1. So using this technique, one can find any improper integral with the help of Gaussian quadrature formula.